Section 6.2 is going to cover error bounds for approximating sums, and there's some really good detailed commentary about this in the textbook. An error bound is a guarantee that an estimate for an integral is off by no more than a predetermined amount. So certainly we want to be able to control the degree of accuracy and be aware of the degree of accuracy when we have to use these approximations to be the values of integrals. So trapping an integral between the underestimate and the overestimate only works for integrals that are monotone or don't change their concavity, right? Because we saw with Theorem 1, Theorem 2, it was very specific about you have to be monotone, or you have to be always concave up or always concave down. So that technique, while useful for some of the time, is not always helpful. So there is a connection between the errors that occur and derivatives, believe it or not. Here's why. So the steeper the graph of a function is, the more error you're going to get in the left and right approximations. And this is true whether the function is increasing or decreasing. So you have some pictures here of increasing functions as well as decreasing function. I took these images from your textbook, so if you do your reading, you're going to come across these. And notice what occurs here. When the line is sort of shallowly sloped, you can see the size of the gaps that are created, which is the error in the approximation. You can see how those gaps get larger as we increase the steepness of the function. Same thing is true on the decreasing side. This is even steeper, and you can see these triangles of error are even larger. So below each graph, you have some details about what the function was and how bad the error is. So you can see in the first situation, the left approximation has an error of 0.125. Second situation, the error is 0.25. Third situation, it's 0.5. And the right approximation behaves similarly. Now, what measures the steepness of a graph? Well, that's the rate of change, which is the slope, which is a derivative. So by taking the absolute value of the derivative, ignoring whether it's positive or negative, because we said we don't care whether it's increasing or decreasing, by looking at the absolute value of the derivative, you will know how steeply the graph rises or falls anywhere at any particular x value. Since the approximation error is larger when the graph is steeper, it's also true that the approximation error is larger when the value of the derivative is larger. So this gives us a way to start to track how significant the error is. Situation is similar when we talk about trapezoid and midpoint approximating sum errors and the second derivative. Because concavity, you should be familiar with the fact that the first derivative tells you if a function's increasing or decreasing. The second derivative talks to you about the concavity. And the more concave up or down the graph of a function is, the more error there's going to be. So here I generated some pictures for you using the Riemann sum calculator that we've used before. And I want you to notice the amount of curvature in the first graph and how it kind of bulges more in the second graph. So again, I've given you specifics here. I did midpoint sums for both of these, and you can see the error for graph A is 0.0052, and the error for graph B is 0.0103. So the more it curves, the more error you introduce. So just like the first derivative measures steepness at a point, second derivative is a measure of that concavity. Since the approximation error is larger when the graph is, again, more curved, bulging, however you want to describe that, it's also true that the approximation error is larger when the second derivative value is larger. Again, ignoring positive or negative signs because we don't care It works for both concave up and concave down. So that gives us this theorem, the error bounds theorem. And if you want the actual explanation for where these formulas come from, again, I'm going to suggest that you look at the explanations in the textbook. But what Theorem 3 says is if you have an integral and you are using these approximating sums, then we know the left and right approximating sums are going to have a certain error bound that we can guarantee. We are going to be able to choose a constant that is always bigger than or equal to the steepness of the graph. And then using that constant, we can calculate the largest that the error can possibly be. And it turns out it's the same formula for both left and for right. For trapezoid and midpoint approximating sums error bounds, we'll choose a constant that's bigger than the second derivative, always. And then we can use that upper limit as a boundary to calculate the maximum error for a trapezoid sum and the maximum error for a midpoint sum. Now these two are different, okay? So there are different formulas here. Again, your book kind of goes into the explanation for why. But note, the constants that you choose, because like I said, we're going to choose those, can be any upper bounds. If you overestimate, the error bounds are still going to work, but your error bounds aren't going to be as good. So generally speaking, you want to pick the lowest constant you can that does the job. You do not want to underestimate with your constants, because then these error bound theorems do not work.